Hey, we're going to do a series of videos here on something a little different. Now we're going to get away from just pure setup discussions, and we're going to talk about dynos and motors and a number of other subjects. So let's get started. First thing, what I want to try and cover in this series is comparing dyno results, and basically talking about comparing dyno results from one dyno to another, and what you should be aware of before you try and do that. Next episode, we'll look at motor timing and boost. Then we're going to have a look at shimming and hall sensor tweaking, effective battery state of charge, and internal resistance. Then we'll do some create some motor models and do some acceleration simulation in RC Crew Chief, so I can show you what you can how you can put all this good dyno information to work. And last but not least, we'll talk about some tips if you want to take the leap and try and build your own dyno. So in all of this, whatever we're doing, we're going to be supporting the information with actual dyno runs, so you'll see exactly what the difference is in some of these effects. So there's a number of different types of dynos. I don't want to get very deep in this because there's a lot to talk about, but basically there's two types. There's a flywheel dyno and an absorbing dyno. Flywheel dyno, what you do is you spin up a flywheel. As you can see here, this is the Mini Pro dyno, and you can see the red in the background. That is the actual flywheel. So what you do is you spin that flywheel up with maximum power applied to the motor, and you measure the RPM, and from that you can infer the acceleration rate of the flywheel, and knowing the acceleration rate you can calculate torque. From torque then you can calculate power. So that's basically how they work. They're actually quite simple, and the calculations are actually quite simple. So Mini Pro, MD2 home builds, the old Robotronic and Phantom dynos, they were all flywheel dynos. You can use flywheel dynos for motor or chassis dynos. Mini Pro makes a nice chassis dyno that I've seen on the internet as well. So all things that you can check out on your own time. The other type is an absorbing dyno. What an absorbing dyno does is apply a load to the motor, and then using a torque transducer or torque sensor, it measures the actual torque directly. So there's no calculation based on acceleration rates or anything. The torque is direct output. So these are used a lot in industry. They're higher end dynos, not something that you're likely to see in the RC world, due primarily to expense. Okay, so next, why do we want to test motors? Well, the probably most interesting part would be determining timing settings so you can get the optimum performance. This is really important in blinky racing. You can see the physical effects of shimming and tuning hall sensors. You can monitor the motor health, so you can tell whether the motor is losing strength, losing power. And you can also compare motors head to head, so you can pick the best. This graph right here shows two motors, or sorry, one motor, and the difference between these two graphs is the red line here, the motor was overheated, and the rotor had lost some of its magnetic properties. So you can see here we've lost power and we gained RPM. So if you were just looking at this on a purely a kV basis, which is kV is the point way out here at the end where you have zero torque and maximum RPM. So you would think, oh gee, this motor is even better now that I've overheated it. Well, in reality it's not, because you've lost up at the bottom end, which is the operating range that you've got is probably from in the middle 2/3 of the RPM range is where you spend most of your time. So you've lost a whole little whack of bottom end torque here. You can see these lines are the torque lines. You've lost peak power. These bell-shaped curves are the power curves. So testing a motor on a dyno can show up these changes and help you make good decisions. When doing dyno testing, one of the most important things is you got to use a consistent test procedure. I use batteries, 2-cell lipos. I always make sure that when I start doing a series of tests that I'm using the same battery, it's at the same state of charge, and I only do a limited number of runs, because as the voltage drops off in the battery, you lose performance. So we'll take a look at this in a little more detail in later series, but you should check your battery voltage after every 4 to 5 runs to make sure the voltage is not dropped significantly. If it's dropped by more than 0.05 to 0.06 volts, then you should stop your testing, recharge your battery back to where it was at the beginning, and then continue testing. The other thing is to monitor motor temperature. As the motor heats up, the armature, or the state of resistance, changes. So if your motor starts getting too hot, it's going to start affecting your results. Normally a dyno run only lasts 2 to 4 seconds, so as long as you're not on and on and on and on 2 to 4 second runs, motor temperature is usually not an issue. So the next thing what we're going to focus on in the rest of this video is comparing dynos. So first thing to realize is performance numbers from different dynos will not be the same. You have so many variables between dynos that to try and get them to be exactly the same, you would have to have very, very tight controls on everything. So if you're using a dyno, it's a great tool for using for your own purposes, but don't go trying to compare with your buddy and say, well, that motor pulls 180 amps on my dyno, how come it's only pulling 170 on yours? Because it's a different dyno. You're probably using a different battery with a different internal resistance, or you may be using a high-powered voltage supply, maybe a completely different type of dyno. So all these things impact. So friction, supply voltage, they all have an effect. So what we're going to do is to illustrate this, we're going to do a comparison between my little Arduino MD2, which started life as an MD2 dyno and has now morphed itself into something a little different and quite a bit better from my perspective, and a Mini Pro, which are both flywheel dynos. One is a direct drive. The Arduino MD2 is a direct drive flywheel, and the Mini Pro is a belt-driven geared type of dyno. So let's check these out and see what we can find out. Okay, so here we've got the Mini Pro dyno. You can see here the red disc in the background. That's the actual flywheel. This dyno uses a gear drive, or a pulley drive, I guess would be more accurate. It has a 2-to-1 gear ratio between the motor and the pulley, so that the advantage of that is that it slows down the flywheel speed, which is certainly something that if you've ever done any dyno testing, when you get up into the higher RPM regime, it's nice to have something that's only spinning at half the speed. So when you're testing low wind motors or something like that, then having the 2-to-1 gear ratio is definitely a good thing. So it's very well made. All the electronics are built into the back here. You can see I'm plugged into the computer, so it's going to data log the run here into the computer, and you can save it, and it'll do the calculations for you, or you can export a file and import that into your own spreadsheet, or something like RC Crew Chief, which we'll be doing in a few minutes. Okay, so I'm going to do a run here. I just got to tell it to start recording, and away we go. I don't know if you can see this or not, but that's the run we just did. I leave the little clear plastic cover off the dyno case just because it makes it easier to slow the dyno down. Otherwise, sometimes it spins for a long time. So here, as you can see, this is the RPM versus time curve. I always run until you get out to a fairly steady state RPM before I shut it down. This is the red line here is the current draw from the motor, so you can see we get very high draw here at the beginning, 108 amps, and then down near the end we're down to just 4.8 amps. Okay, so that's what I want to show you here. Next we'll do some comparisons, and you can see what the difference is when you're using different dynos. Okay, we've switched over to the MD2, the Franken MD2, using the same ESC, same receiver, same battery. Battery's only done that one run that we did on the Mini Pro, so the state of charge is pretty much identical, maybe slightly lower, but nothing significant. So here you see the remnants of the MD2. So what I've used is the motor mount, which is nice and easy. It's just a clamping system, and some shims to raise it up so I could use larger flywheel. So this is the larger flywheel. It also has a different sensing or encoder wheel on it to block and allow the light through. Over on the other side here, this is the Arduino. It's essentially a microcomputer. The top surface there is all the interface circuitry to, this is the plug-in from the MD2. It just plugs into the circuit board, so that's uses the infrared emitter and detector that's down at the bottom here, and the rest of the circuitry is to for current sensing and voltage sensing. Okay, don't want to get into too much details there. We'll talk about this a little later on in another episode, but I just want to do a run here and show you what it's all about. So on the screen there's a little program that I wrote to communicate. So this communicates with the Arduino and brings the data across. So if I just hit start recording and pull the trigger, turn my radio on first, then we should get the result. Okay, so that's the end of a test. You'll notice that the test went significantly faster than the Mini Pro, and the reason for that is the inertia of the flywheel system is quite a bit lower than what the Arduino. It's roughly well, it's less than half the inertia that the Mini Pro has. Okay, let's do some comparison. We'll go into RC Crew Chief and compare the dyno results. Okay, so now we've completed our two tests on the two dynos. Let's analyze those results and see what the differences are. So we're going to open up RC Crew Chief in our motor manager, go to the dyno analysis page, and we just got to load in the files. So let's load in the Arduino first, the MD2, and this is a generic file, so we have to select the dyno file type. One of these days I'll get ambitious and make my life easier and make it an automatic import, but not today. So you just have to go and select the which header represents which line or column of data, and then you get this graph of KRPM versus time. So this is starting at 0, and the motor's accelerating the flywheel until it gets to its maximum speed. So to do the dyno analysis, I just need to select the range of data that I want to use for that analysis. So we just need to go up to a point where the RPM isn't changing very much. The other thing I need to put in here is my flywheel inertia, so I know that my 50 millimeter diameter flywheel has an inertia of 63 millimeters squared. So once I've got that, then all I have to do is click Dyno Calc, and there's my graph. So this is the power. The red line is the power, the green line is the torque, and the black line down here is the efficiency. So we want to do some comparisons, so I'm going to add this to this little box down here so we can compare the results between the two dynos. Now let's load in the Mini Pro. So I'll open that up. Now this one will automatically import, so just go import data, and there's our RPM graph again. So it's very similar to the previous one. The big difference between these two is this is a slower acceleration graph because the flywheel inertia is quite a bit higher than my little 50 millimeter wheel. So have to do the same thing here. We just need to grab a range of data that we want to use in the dyno calculations. Now you'll see here the MD or the Mini Pro actually inserts a flywheel inertia value to use, so I don't have to change that. And then we just click Dyno Calc. So there we are. We've got a nice smooth graph. Very good data. I do use a data smoothing technique, which helps to take some of the jaggedness out of the data, because we are calculating our acceleration based on speed. So there is some issues that arise with that, but with a little bit of data smoothing, you can get a very nice smooth graph, which is what you would expect. So let's add this to our list, and now let's do a comparison. So here we've got our comparison graph. We can have up to 4 different dyno files in here that we can compare head to head. So let's just go ahead and click and see where we're at. So here we've got the red line, which is the MD2 Arduino, and the green line is the Mini Pro. Now when I first saw this, I was expecting there to be a difference, but I wasn't expecting it to be quite this much. So the first thing I looked at is I'm thinking, okay, it looks like we have a difference in, or something to do with the inertia, because our power values are down quite a bit. So what I did was I went and did a fairly detailed calculation on the inertia of the flywheel, and I came up with a higher value than what was reported in the data file. So what I've got is 177 excuse me, kilogram millimeter squared. So if we change that value and then just do our dyno calc again, we're going to get more power. So let's add that and do our comparison again, and this time we'll bring in both of them. So now you can see our blue line is the power with the higher inertia value. So we're still quite a bit out, but you would expect there to be some difference because we've got a belt drive which has friction, we've got bearings which have friction, larger flywheel which has more aerodynamic drag probably. So there's a number of things that can contribute to that. So if we look at our torque curves, you'll see there's almost a direct offset in the torque. The difference in the torque throughout the range is fairly consistent. So being able to modify my program, I thought, okay, well, let's see what happens if I just put in a torque correction factor. So what I did was I added this little guy here, and I can just add a 13 Newton millimeter torque offset, do a dyno calc again, and add this, and then do our comparison. And now let's just look at the final one. So now you can see we're fairly close. The reason for the difference is the torque offset is probably not constant. It probably has needs a little bit more sophisticated equation to model. But anyways, you can see we're in the same ballpark. Our peak torque, our peak power is in exactly the same range. The torque values, you can see that the shape of the torque curves is very similar. So for two completely different dynos, we've got very similar results. And as long as you're not trying to compare one dyno to the other, this is all good. Okay, so that's all I want to talk about in this episode. Up next, we're going to look at comparing testing motors at different timing settings, and hopefully do a little exploring with boost.